filters will be initialized in the beginning with, let's say, 10 5x5 filters. Each of these 10 5x5 filters will be initialized with 25 weight values. And then, as the backpropagation occurs, each of them independently change. So, in fact, by the end, a filter has a single set of numbers, but the filter behind it will obviously have a different set of numbers. And the filter in a different layer, of course, has a completely different set of numbers. Okay? Any other questions? Okay, good. So in fact, I can send you the link to this particular video. This is Andre Karpathy explaining the AlexNet calculation. And then he actually calculates essentially the number of weights given these particular parameters that I mentioned in terms for each layer. Okay, so for example, given our answer, given our discussion, so the kernel size 11 essentially means you need 121 weights per filter. And if you have 96 filters per layer, then you need 96 times 121 weights that needs to be learned. And those are called the parameters. Okay. So I also already mentioned the deepening war business, that in fact things have basically gone from AlexNet, which was way back in 2012, to InceptionNet, to ResNet, but essentially that's where the images are. So what I'm going to do now is basically try to go from here to sort of make clear to you that much of this is just about images. And there's a bunch of ideas that work here which only work for images and may not work for anything else. And what have people been doing? So in fact, if all you have is a hammer, you should look at everything and think it looks like a good name. Okay, and so clearly this technology seems to be working on images and people are impressed, and so people are trying to use it in all sorts of different places, but clearly it makes sense for images and nothing else, honestly. Okay, so here's something that I want to mention. This I mentioned it several times before, in passing probably, and maybe in some of the classes, some of the talks that I forced you to do. By the way, those talks, the initial talks that I made you watch in the beginning of the semester, you can actually watch them now to make a lot more sense, because we actually know what convolutional networks, etc. So, Hinton back in 2015 was giving this talk, and he essentially said, okay, the neural networks are working better, and why is it working better compared to like late 80s and early 90s to now? And he wrote this bunch of reasons. Okay, the reasons, of course, are some theoretical reasons, some practical reasons. Okay, and the theoretical reasons, of course, by now you know, start with good initialization. Behavior initialization is something that we talked about. Start with a different kind of thresholding units. ReLUs seem to be actually better because ultimately they keep the gradient from becoming zero. Many things that neural networks care about is keeping the gradient signal from disappearing. ResNets basically make the gradient signal go faster to the back layers. Okay, ReLUs make sure that the gradient doesn't become zero, because in sigmoids, etc., you essentially will have flat spots of two. Okay, and then use good techniques to avoid overfit. And the idea is drop out. You know all three of them right now. So you know all the theory, right? And on the practice side, while we were figuring out what the heck to do with various kinds of neural networks, right? Not we, I wouldn't say we, Hinton was figuring about this, and a couple of other things. The world was changing slowly. Okay, for example, cell phones were invented, which increased the number of cat pictures on the internet exponentially. Right? Basically, now you have cell phones, essentially, everybody is taking pictures of everything. You now live in this world where there is no public privacy. Like you could be an anonymous public person before. Now you try, picking your nose while walking on the Orange Mall, there will be ASU now, faculty member does this, right? Everybody has these pictures. And so millions and millions of these pictures. It would have been hard to actually pay people to take these pictures. Now they just want to do it themselves. On top of it, there are surveillance cameras. On top of it, Google, how many of you have seen Google Streetcar going by and seeing all sorts of funny things where somebody was picking their nose while Google Streetcar went by? He wasn't even actually watching on the road. This is the damn car that passed by, but again, they would be funny pictures part of the internet. The big thing to remember is the word changed. it's actually very hard for us, mere mortals, to figure out how the world will change. And I gave this example in one of my talks that you may have heard, that how many of you have seen the original Blade Runner? Not the 49, which I haven't yet seen. Okay. Definitely you should see the original, I believe, also the next one. But the original Blade Runner is, of course, the progenitor of all the great movies, connected to AI. And they were thinking about future where essentially androids are indistinguishable from humans. They were thinking about cars going between buildings, flying, etc., etc. But if you watch this movie again now, notice that their TVs are still huge, big bricks. The imagination sort of failed there. Their phones are big bricks again. How many things can you figure out? The society changes in all dimensions simultaneously. It's not like, let's give Hinton a chance to figure out how backprop works and then we'll start changing the society. No, society just changes. And sometimes we will actually do things that because the society changed are no longer even useful. Science is full of problems that people actually found a solution, but the problem went away. And so you don't need the solution anymore. Sometimes the society changes in such a way that your problem becomes actually more easy to solve. That's actually what happened for machine learning, essentially. Okay? The huge big thing is data is available on the net. You keep hearing people saying, we are producing trillions of bytes of data. So as if our foreparents basically were bozos, just sitting there, not producing data. They were producing data. Nobody was taking pictures of them producing data. Right? You think, my other example is, you think United wasn't dragging people through the aisles before? They were doing it all the time. You think police weren't basically hitting people of different colors with different intensities? They were doing it all the time. We didn't have a picture of it. Now, my God, don't do anything because there's a picture. So maybe our society will evolve to a point where we will stop doing anything because we are afraid that there will be a picture of us doing that thing. But right now at least, there are lots and lots of data available. It's being essentially captured. The data was always being produced. It was not being captured before. Now it's captured. And that becomes very useful because it turns out that these are ideas. It's like, for example, imagine somebody told you that coral, the coral thingies, I forgot their actual scientific name, produce coral reefs. So you said, let me check this out. So I get a couple of those, funny things and put it in my fish tank, wait for 2-3 days, and see if there is a barrier reef. If there isn't any barrier reef, I'm very disappointed. I think this is fake science. Okay, basically, if people are just making this stuff up, clearly nothing is happening. Do you understand what I'm saying? That is, in essence, what was happening for neural networks, because, at least for the perceptual images, because in essence, it turns out that with enough data, you could actually learn the bits. It's mind-boggling, just as mind-boggling as a coral reef being formed by these little creatures. But it's actually possible. And we couldn't even have tried this out until the society itself changed such that the data is being produced and captured. Now we get it. Okay? And then of course there is GPU stuff. Of course, if you ask Jensen Huang, he thinks all this other stuff is nonsensical. The most important thing is GPUs. That's actually useless stuff. In fact, you will notice that GPUs may or may not be all that important as we go forward. I don't know how many of you have kept track of AlphaGo 0. AlphaGo 0 uses much fewer TPUs, tensor processing units, than AlphaGo before Lisedol. There are algorithmic advances that are actually reducing our dependence on GPUs. So I clearly won't get any research funding from Jensen Huang, but I think GPUs are important, but nowhere near as important as the entire society changing and taking pictures of each other and recording everybody and essentially putting everything on the web. And then it's searchable and it's usable. You guys should be like really scared about it. But as AI people, we are happy. We can learn stuff and we can then say, yeah, this person is a terrorist, this person is not a terrorist, because we have large number of terrorist pictures, labeled examples. And so we get to essentially do this kind of crazy stuff. We could not even do before. Okay? So let me complete this and say that it turns out that about only 100x in 2015 came from the theoretical advances, and 1000x speed up came from just the society changing. So if you just sat around and tried, so this is it's very important. If you are ever doing research, write all the ideas that you had that didn't work. Don't throw them away. Put them in some Google Doc somewhere. I think Google Doc is probably, Google may not be there by the time, but put it somewhere such that you can find a time capsule. And about 30 years later, go back and see, let me try this idea again. It might actually work. Because the world has changed and the idea might actually work. That's pretty much what happened. These people just sat down doing none of this. It would have worked with 1000x speed up. And trying is more important. Okay, mostly we just give up saying, it won't work anyway. And that ultimately winds up becoming a bigger problem. Yes, there was some question. Yes?
I'm just going to say, we're going to start predicting like terrorists based off pictures, and terrorists will just start looking different.
True. I mean, again, we are smarter than our machine learning algorithms also, I hope. Okay, but that's a very good point. But I won't dwell on that right now. So let me do a few more things. One is the transport learning part, which I already mentioned. I'm just going to repeat this. Which is that ConvNets and general neural networks require a huge number of examples, training samples to train. ImageNet currently has more than 14 million images. Now, if you have a custom image classification task, but which you have much fewer examples, such as radiology that I mentioned, then even though in theory neural networks should be able to find the patterns, there are not enough examples, so they won't. Again, my coral reef example. Okay? So the question, of course, one thought is perhaps maybe visual systems sort of develop to find the same sort of low-level features across various kinds of images. Doctors, I'm going to tell you something very important. Doctors are people too, right? So they do actually develop their visual system evolutionarily without knowing that later on they will become radiologists. Right? So they're pretty much probably using some of the same feature extraction things that they actually figured out. Okay, so the idea would then be that if that is the case, in a neural network of, let's say, something like this, maybe these things are essentially capturing some sort of features, especially the convolutional layers. So what I can do is actually take just that part and the weights for those, and you call that a pre-trained trunk. You should know this to impress your employers, right? Pre-trained trunks, So if you say, how do you deal with smaller number of, I'll just get one of these pre-trained trunks. And the pre-trained trunk is basically like lobotomizing and taking somebody else's part of their brain, essentially. Okay? And then on the bottom of this pre-trained trunk, then I'll put some more layers, and then put an FC layer. Notice that the FC layer here, the FC layer here would be saying 1,000 different classes. One would be dog of type 1, another is a dog of type 2, etc. Right? The FC layer here, if it's radiology, and if you show, a neural network that's supposed to, basically predict radiology, based on the radiology images, whether or not certain kinds of cancers are present, and if it says cat, dog, human being, as the top 5 examples, it will be very hard to get venture capital funding for that idea. Right? So at least you will have to change the FC layer such that you will actually say the classes that you are trying to learn. So then, right now you have this huge, big, deep network, but then now I'm going to show my radiology images at the top. They will get through here, they will become some random higher level features, and then these layers, both convolutional and fully connected, will learn the weights there. So in the backpropagation phase, you are essentially fixing all these guys' weights. You are not letting them change. It's completely up to you. You decide whether to change a weight or not. It's not like, the network will just change by itself. You write a program to change whether the weights are changing or not. Okay? So in the backpropagation phase, you keep these guys unchanged and only retrain these weights. This reduces the number of parameters that you are trying to change. And so much fewer examples might well help you learn the patterns. Impressed? So here's my point. You guys all came into this world with a pre-trained clock. You know, if you have learned anything from basically, early childhood neuroscience, infants, I may have mentioned this, is one of my favorite examples. Infants, right after they are born, if you just lurk around in the hospitals, right, they don't catch you, you go an infant that's like 1 or 2 minutes old, and then try to put like a banana in front of this boy or girl's nose. Okay, they'll show happy face. Then you put rotten egg, smell, they'll do that. What the heck do they know about bananas and rotten eggs? How did they figure this out? They had a pre-trained trunk. Who was pre-training our trunk? Evolution. Okay, that's a way of thinking about it. Okay, so again, these are sort of facile analogies because obviously brain is way more complex than a silly 150-layer neural network. But we do come into this world with a large number of weights of a large amount of our structure set already. And that's one of the big things that we're trying to figure out, how much do kids actually know and how much do they really. In fact, there are some other crazy things, for example, such as kids, they show that very small kids, if you throw them into the water, it's bad enough that you're showing them bananas and rotten egg smells, but if the hospital staff is still forgiving, then you try to throw the kid into the water. And they will make right kind of, swimming movements. And about 3 months later, you again throw them, they'll sink like a stone. By the way, none of this I'm telling you to do. Okay? But what is happening is essentially these networks come in, So in fact, it's crazy to say, I will get a pre-trained trunk. Pre-trained trunk is some neural network's anterior brain. And it makes sense only if you really believe that the features are likely to be the same for both the tasks. And what is interesting is, mostly people are looking only for image classification tasks. And for image classification tasks, they're just images. And so when they say transfer learning, it's never the case that they take a 150 layer. So this is what I told you right now. You understand this. The same thing in the public. They think, well, there is a 150 layer network. They can take the trunk of it and they can train it to figure out, for example, how to do math, or how to predict whether or not there will be rain tomorrow, or how to see whether there is cancer, even if in fact the inputs for those things are no longer images. Do you understand what I'm saying? Because that's where the public falls flat, because they just assume that all tasks have the same structure. No. Visual tasks have similar structure, and so that's what you are exploiting using the transfer learning. If you can understand that, you are that much closer to reducing the misinformation output. Okay? But it's a good idea. So note that this only is empirically shown to work for image data. Okay? And no theoretical proof, actually. And so, in fact, pre-trained trunks for different kinds of convex are available right now, and this is basically the reason why large number of people now can start machine learning startups. Okay, and then say, oh, so you have 15 images of some particular kind, oh, fine, we'll just take some pre-trained trunk and then add your 15 images in the bottom and just train a few parameters, and we'll say we have built deep learning. Okay, that's not even it. Okay, so that's one great idea. The other great idea actually, again, which is very, very connected to images and it's useful to understand, is this notion of data augmentation. Okay, if you don't have enough data, can you increase the amount of data that you have? Okay, there, once again, this actually works, and this is data augmentation is very domain dependent. Remember Shakespeare said, a rose by any other name doesn't lose its fragrance. A cat by any rotation doesn't lose its catness. Right? So if I have a cat image there, I basically crop it into lots and lots of small cat pictures. Those are extra examples for which I don't need to ask humans, is there a cat in it? Because I took the cat and I cropped it. So it must be a cat. I took the cat and I turned it by 1 degree. It must be a cat. 15 degrees, it still must be a cat. This is darned obvious to you guys. Right? But it increases the amount of data available training, 100-fold, 1,000-fold. Because as far as the network is concerned, it doesn't understand that this is a cat that is rotating. It is a completely different image with different intensity values at different places. So there are actually two very useful things that happen because of the data augmentation. One is you increase the amount of training data that you have available. Right? The other is actually it reduces overfitting. Remember, overfitting is one of these problems for machine learning algorithms. Okay, so you should be able to recognize cats from different poses. There's very little market. If at all there is market for people who can recognize cat pictures. There's even little of it for people who can recognize cat pictures only if they are held straight like this. If you turn it a little bit, I can't see. And if they learned only that part, that means they overfitted to a straight standing straight cat. So it reduces overfit. Another very nice idea, it's no skin off your nose, it's so easy to do. Once again, people say, if all your life is just image data, you think both this kind of transfer learning and this kind of data augmentation are universal ideas. But they are by no means universal ideas. Imagine, I give, instead of this, I give like a bunch of text, okay, and a review for a movie. And the classification is, it's a positive review or negative review. This is what's called the sentiment analysis. Can I augment that data by this kind of nonsensical thing? In particular, take a picture of the text and then turn it around. No. Even otherwise, can you think of other data augmentation techniques? The more obvious one would be throw in a few extra words here and there. You can throw one word into an otherwise beautifully positive review, which at the last minute changes the entire review to be negative, and we all understand it, and the neural network does that. So data augmentation is completely domain dependent. It works for image data. If all you want to deal with is image data, which is fine. And to give credit where credit is due, one funny thing is for humans, a huge part of our brain is essentially used for visual processing. You actually notice this in the analogies we use. When you understand something, you say, I see now. What is there to see in calculus? Right? But somehow, basically, we do everything as if it's a visual task. Brain just evolved that way. Okay? And in fact, there have been other kinds of great neuroscience experiments where they make the visual cortex do other things. But anyway, the point is, people do feel that people tend to forget that things that work for visual data may not actually work for everything else. Okay, this is again one of the things that I mentioned in this very beginning task that I made you do, which is we are coming to a point where AI systems are able to do perception the way little kids can do perception. But little kids don't actually get Google jobs. Although apparently that's changing. There is a 17-year-old who wrote this paper, it's apparently a subject like now. But most little kids don't do, they still have to go through 25 years of college before they can be useful at all. Or at least that's what I believe, right? So the point is there are a lot more things to intelligence than just being able to see cat and dog images, or even radiology images. You don't get paid at all for seeing cat and dog images, huge jump, but if you can see like a radiology image and say this is the particular disease, you get paid. Those jobs unfortunately will be out. But in between there's a whole bunch of other things that we do which have nothing directly connected to visual processing. For these ideas, we have to be careful as to how to use them. Okay? So deep learning for non-perceptual tasks, right on demand. which is basically the biggest successes have been for vision, speech, and to some extent to NLP. NLP not completely, but NLP is natural language processing. But it's really worked very well for vision and speech. And those are also things, by the way, where our theories of how anything happens in vision and speech are all bogus. Basically, you may as well let neural network come up with something. Okay. However, it's not actually all that useful yet for many other tasks. But if you want to get somebody to pay you money, you say, I use deep learning. Then you'll get paid money. Deep learning with full 2 layers. Still deep learning. Nobody needs to know how many layers your network has. Okay? So I'm not kidding. So in most areas, in fact, input, and furthermore, in many tasks that we actually engineered our society that we live in, we actually understand how many things work. It's not like we were born yesterday. Right? You don't need the network to figure out. You don't know what makes a cat a cat. So you couldn't tell the system what is a cat. But you do know what makes a grade in this class. It is based on your homework score and the exam score and the project score. So for me to say, I won't give that information to the network, and I let it watch the temporal tube of this entire semester. You know, a series of pictures and voice and video of you coming in and going out and sleeping and not sleeping, and then after about 1 million years, this guy figures out essentially, yeah, there's something like homework that seems to be important. Why do that? There is doctrine here. It's a domain that we created. We should be able to use the features. There's cases where you don't know the features, there are cases where you do know the features. So that's like the place where I happen to know the filter. I want to put it in. And some of the craze for let's do everything from scratch essentially makes people kind of reinvent things that are not actually required to use. So an example, this was actually something that I was talking to in Johnson Controls. Those guys got all excited because DeepMind essentially said, after AlphaGo, they need to kind of tell Google that, you know, Google isn't paying them just to play Go, right? So they said, look, we now have reduced the energy consumption in the data warehouses by a significant factor. And did we mention we use deep learning? And then this was, of course, if in fact anybody in DeepMind sneezes, there will be 18 articles in front of us. And if they sneezes and say deep learning, it will be 25 articles. And so there are lots and lots of articles. So Johnson Controls asked me to kind of find out what exactly they did. So this guy, Jim Rao, wrote a little actual paper, not even a paper, it's a PDF thingy, something on the web. And what he did essentially was he had 5 hidden layers, 50 units per layer, and he used these hand-selected features. If you say hand-selected, people lose interest. If you just use it and don't say, people will be very happy. Because it's AI there. You see what I'm saying? But not using these features is difficult. Because these actually people know are connected to energy consumption. So I think this guy deserves credit because he said what he did. On the other hand, the media and the bozos who think he was just somehow seeing patterns where no patterns exist and just looking from the temporal tube, what is the best way to control energy, those guys on the other hand need some psychiatric counseling. Right? But it's worthwhile keeping this in mind. So, probably the last thing that I get to do today's class, and it actually just came in time because yesterday, Kaggle, how many of you know Kaggle? See? So Kaggle basically put out this survey, right, about what machine learning techniques people out there are using. And that is the answer. People in data science industries are using, as against New York Times, the papers are saying. And so, you notice what's up there? Logistic regression. Okay. How many of you think we did logistic regression in this class? Humor me, guys. We did, okay? It wasn't, again, you also didn't care. Why do we care about logistic regression? Let's wait for the deep learning to come. That's when we know what's going on. Logistic regression was perceptron unit with sigmoid function. That's it. That's logistic regression. We said this, we did this. It was just so uninteresting because you were waiting for 150 layer networks to come. That is what you are using in the industry right now. So in fact, Tom Simonite, who is this Wired reporter, tweeted that, hey, maybe I should be writing a lot of articles on logistic regression. It's actually the thing that people are doing still. And there's a reason, because logistic regression makes a lot more sense when you actually know the features for your domain. Why know a domain, know what matters, and say, I would not tell my learning system what matters. Let it figure it out itself. Why? What purpose, pleasure do you get? Other than in tests when I do that to you. Why would you do this for your learning system? What are you trying to prove? Do you see what I'm saying? So I hope you understand that there is that particular distinction. It's not that neural networks are not being used. In fact, we also, by the way, there are a couple of other things that we could have done in addition to CNNs, RNNs. Again, just like the original CNN idea, RNN, recurrent neural networks, essentially, we may talk about this at some point of time when we talk about dynamic Bayesian networks, but essentially, they are more useful for natural language processing. They're useful for sequence data. Okay, so anytime there is a sequence data, there is a temporality to the data, some kind of a structure of time is needed, recurrent networks do that. And this is this other place where essentially original ideas for recurrent networks came in Schmidhuber's lab many years back. It didn't work, just like this coral not forming in your fish tank. And so people gave up on it. And then they rediscovered it after everything started working. And so the last thing I want to tell you is Schmidhuber. How many of you have heard of the name Schmidhuber? Okay. How many of you have seen the movie Amadeus? Okay, do you remember the very first scene in Amadeus where Salieri, my God, why would you see it in the movie and not remember the first scene? But Salieri basically plays this, music that he made and asks, do you remember who, can you recognize who the composer is? And they don't recognize. He plays another of his piece. He asks, do you recognize? He says, I don't recognize. Then he plays one of Mozart's pieces. Do you recognize? He says, of course I recognize. So if I, instead of Schmidhuber, if I ask Geoff Hinton, how many people would have raised your hands? Right? The reality is, Schmidhuber is this poor guy who did do a large amount of work, but it sort of got an overlook. Plus, he developed large amount of, bitterness because of that. So there is this joke that I will end the class and this entire deep learning discussion with. Some months back, somebody on Reddit was asking, I have this idea for machine learning. And I don't know whether or not it's been tried. People come up with various ideas here. How do I figure out whether or not it's been tried? And there was this girl who had a killer answer to it. She was actually in the Google Mind intern. And what she said is, there's a pretty standard procedure for it. Okay, what you do, you send a mail to Schmidhuber saying, I came up with this idea and I asked Jan LeCun and Geoff Hinton and Yoshua Bengio, and they seem to say that they have done this already. Is this true? And then you send the same mail to